Welcome back. In this video, we are now prepared to study systems with complex eigenvalues. So recall that we looked originally at homogeneous, constant, coefficient, first-order linear differential equations and second-order differential equations. One of the things that we'll notice here is that when we are finding these eigenvalues, they actually correspond to the roots that we would find in our guesses e to the r1, e to the rt for second-order differential equations. The cases that we've considered are where we would have two real roots, where we would have one repeated root, and where we would have two complex roots. So the first case we have already tackled with respect to systems. The next two cases are really similar to that of second-order differential equations. We won't focus on the one repeated root, but we will look now at two complex roots. So imagine we have a system. This is a first order, homogeneous, because there's no plus g of t tacked onto the end of these guys. First order homogeneous, constant coefficient, linear systems of differential equations. And we have to be this specific because if any one of these features changes, for example, constant coefficients, then our methodology doesn't really work anymore. So A, B, C, and D could, in theory, be functions of time. So A, B, C, D are all real numbers. Further, suppose that the system results in complex eigenvalues in which it is the case that lambda equals g plus or minus hi, where g is the real part and h times I is the imaginary part of the eigenvalues. Then the general solution is this big gigantic mess. We won't derive this, although I do have a derivation I could share if you are interested. But let's look for a second at what this means by g plus or minus hi. So for example, if I wrote 3 plus or minus 2i, 3 is the real part. So g is 3. And this is the real part. And actually, I really should say h equals 2 is the imaginary part. Okay, and so what we mean by I is a lot of times when we take the square root of a negative number, for example, times where some point in your experience when you use the quadratic formula and you had something like negative 3 plus or minus the square root of negative 64 over 2. And what we would do with that negative 64 is we would break it up into two factors, one being negative 1 and the other one being 64. So now what happens with that is if you take the square root of a product, that's identical to taking the square root of each of the factors in that product. So the square root of negative 1 times the square root of 64 over 2. And the square root of negative 1 is what in mathematics we call I. It stands for, it's an imaginary number. It still occurs in real world situations. Square root of 64 is 8, so we could write this as negative 3 plus or minus the square root, negative 3 plus or minus 8i over 2. So let's delve into this. You can see a lot of these components in here are coming from either the system of differential equations or the eigenvalue. Notice that we don't directly use any of the eigenvectors in here. They're already taken care of. So you do not have to worry about grabbing the eigenvectors. We only need the eigenvalues. So notice that A, B, C, and D, A is a component that gets inserted in certain spots. B is a component that gets inserted in certain spots. And you can see those guys there. C and D, however, do not appear to get inserted into this equation, and that you might say, well, they don't matter, but in fact they do matter because A, B, C, D is the matrix that we use to compute the eigenvalues in the first place. They just don't directly fall into the result. The other thing to notice is that the real part, G, ends up being an exponential coefficient. So it could be positive, it could be negative, and you could see that if this would be e to the positive something t, then this would result in exponential growth, And if g was negative, then we'd have some sort of aspect of exponential decay. The h, and g also kind of happens to go into one of these coefficients here as well. Now, the imaginary part, h, actually controls the frequency of the sinusoidal components of these functions, and also happens to go in as a coefficient. But most importantly, notice that h, the imaginary part, is going to control how rapidly the sine and cosine functions oscillate. So let's consider a system. Here we have dx dt is 3x minus 13y, dy dt, little dy dt, is 5x plus 1y. And when we compute the eigenvalues of this, we notice that we get lambda 1 is 2 plus 8i, and lambda 2 is 2 minus 8i. Notice that they're identical, except that one has a addition sign, one has a subtraction sign. These are what we call complex conjugates. And they always come in pairs. So when you'll always notice that for a system, you're going to have the real part, g plus or minus hi, will cover both eigenvalues. So to piece this all together, the first thing we should do is identify what the components are. So we know from the matrix that A is 3, B is negative 13, C is 5, and D is 1. We know from the complex eigenvalues, here we have G, here we have H. Notice that H is always going to be, we're always just going to take the absolute value of the H. So up here in our definition, we say G plus or minus HI. So H itself is going to be a positive quantity, but it's going to be added in one of the eigenvalues and subtracted in the other. So we are just going to, for G, we do take its sign. In this case, it happens to be positive 2. H, we ignore the sign, it's going to be 8. So now really what this boils down to is plug and chug. And so the y vector, recall what that has in it. That's just our two dependent variables. So x and y equal. And now we can start plugging things in here. So we'll have k1, that's our arbitrary constant, e to the 2t, times, inside the parentheses for the x component, we'll have cosine of 8t. So h is 8. And for the bottom component, we'll have negative a plus g over b. And that might be something I want to do off to the side, so I don't have to keep writing in that big fraction. So let's go ahead and just write that down, figure out what that coefficient is, and then worry about plugging it in. So that's going to be, let's see, negative a plus g over b. That's going to be negative 3 plus 2 is negative 1. Negative 1 over negative 13 is 1/13. Okay, so this coefficient here will be 1/13 of cosine 8t. Also, the other thing I'm going to need is h over b, which is 8 over negative 13. Oh, I'm sorry, now that's not h, that's h over b. So h over b is going to be 8 over negative 13. So here we're subtracting it, minus h over b, so this will be plus 8/13 sine of 8t. And that completes that term, plus k2 e to the 2t, g is 2. And a lot of this stuff is going to look very similar, except the top component is going to have sine of 8t, and the bottom component is going to have the same coefficient as the cosine did here, 1/13 sine of 8t plus h over b. We said h over b was negative 8/13, so we're adding it, so plus negative 8/13 cosine 8t. All right, and we could split this up into the x function and the y function. So let's go ahead and do that just to demonstrate. Now the y component looks really tricky, but a lot of these terms that are as a result of the eigenvectors, and the eigenvector I intentionally chose to make the top component a little bit simpler, only because we'll see in a moment that for spring mass systems we can decompose the system into a system of two differential equations, one of which will represent position and the other one which will represent velocity. So if I now distribute this through k1 e to the 2t times cosine 8t, and this should look familiar from working with Laplace transforms. We came up with these types of solutions with Laplace transforms as well as with second order equations. And here we'll have plus k2 e to the 2t sine 8t, and that's the entire solution. So for a spring mass system, that's a very likely solution where you have damping and end up with complex roots. And the bottom component is going to be a little longer. It's going to be y equals, now k1 e to the 2t gets distributed to both terms here in the parentheses. So k1 e to the 2t, well, the 1/13th I'll factor out, 1/13th, and this is cosine 8t, that's the first term. Now distribute to the second term, that's going to be plus 8/13 k1 e to the 2t sine of 8t. I'll do the same thing for the second guy here, k2 e to the 2t distributed to the 1/13th sine 8t. So 1/13th k2 e to the 2t sine 8t, and then distribute it to the minus 8/13th cosine 8 to the t, or minus 8/13th cosine 8t, which will be minus 8/13 k2 e to the 2t cosine 8t. And that's the full-blown solution. Now, to find initial conditions for k1 and k2, this can get a little cumbersome because we would need initial conditions for both x and y. And so once we substitute in our t equals 0, we're going to get a pretty, I shouldn't say ugly looking system, because of the sign of 8 times 0, those will go away. So we'll get a system of equations here if we get an initial condition. And a lot of these terms will reduce when you plug in t equals 0. So you'll be able to solve for k1 and k2 pretty quickly. Now, this would not have been so easy with working with second order equations where you actually had to take the derivative of this big mess. Yeah, so anyway, that is the solutions. The reason I wanted to write this out in particular is because the first thing we should notice is in this solution, and if we just kind of thought about the 2 as the g and the 8 as the h, what we're noticing is that g controls the amplitude. So if we have something like this, if we have g is greater than 0 for this system, then for both x and y, what we would observe is that, well, if g is bigger than 0 and all I have is an exponential times a cosine and an exponential times a sine, they're all have the same frequency. So what I would see is if g was bigger than 0 like it is here, is the oscillations would progressively get exponentially larger. And we would see kind of something like this, versus if g was less than 0, that would mean we'd have like e to the negative 2t, and that would be an exponentially decaying sinusoid, and that would look more like this, something we've seen before. And again, exponentially decaying amplitudes, we would see that we could contain that. Now, one other case, what if g is 0? Well, if g is equal to 0, that means the exponential piece is e to the 0, and you're just left with 1 times cosine 8t, 1 times sine 8t, with the k1 and k2 in there, of course. Those will just control initial conditions. But with g equals 0, the exponential piece is just 1, and so there is no exponentially changing sinusoid. It just oscillates. It's basically the equivalent to saying no damping at all in a spring mass system. So as a result, that helps us think about what's happening to both x and y, because x and y are both doing this. They're both doing the same thing. It just so happens that y has more terms in it, but they are all same e to the gt cosine ht or e to the gt sine ht with just different constant coefficients.